All right, we'll start. All right, cool. Hey guys, thanks a lot for joining. Thanks for joining. It's Monday night, and last week around the same time, we started. We were all complete strangers to everyone, and now though it's been a week that we have worked together, it feels like we have known a little more, better about each other. All right. So why are we doing this within quantum computing India? We have now four verticals, or we can't even say four verticals because quantum hardware kind of is a horizontal thing, quantum machine learning is a horizontal thing, quantum finance and quantum cryptography could be two verticals, right? And there's Pinaki, Anuruddha, Hirme, and Sabin, who's been helping us in terms of curating and creating courseworks that will eventually be launching for the students of India. All right, so this whole idea of having, because essentially when we selected apprentice, the whole idea was to learn, right? To accelerate learning, one way is learning from each other, and there's a lot of research that has been done around this. One quick thing is this, so what we call the pedagogy is essentially a 17th century concept, right? Where there's a teacher and it's a one-way thing where the teacher teaches and the consumer learns from that. Then in the 70s, 1970s, it kind of became this facilitator-led thing, right? So where the teacher was supposed to act like a facilitator, we're guiding the students in the right directions. And since 2000, because of internet, it has become more like a teacher is a learner and the learner is a teacher, right? So this part I'm talking about. Now, maybe our Indian school systems haven't adopted that fast. And looking at the new education policy also, it looks like we are going in that direction, but like pretty slow, right? But since we are kind of operating outside the realm of maybe the startup space or even the educational institutional space, I think we have a little bit of leeway to quickly adopt new things that are coming up and then use it to our advantage, right? This is something that we have been doing with other communities, other skill-based or learning-based communities that we are building, where we see this working really well. So we have something called a facilitator series where people with experience, be it on the industry side or on the academic side, come and share their knowledge with us. That's one, which is what we are doing within QCI on Saturdays. Right, so we do Saturdays 4 to 6 p.m. We have the knowledge series, which is essentially by practitioners and academicians who are experienced in the field. Then, so when we started this whole thing, apprentice thing, and every week we said we should have a learning outcome. Now, this learning outcome was initially suggested that we'll have a blog that's written by each team. Okay. But then while we were discussing, especially the hardware team, we were discussing, and then, hey, not everyone in India or within our community knows about hardware. Why don't you guys give a quick talk about quantum hardware 101? And then that's how this whole thing started. And now because of this and looking at the kind of response that we are getting when we pitched it to other communities, other verticals within us saying, hey, this is something that we are doing in quantum hardware, would you be interested? And everyone said, yeah, more than a blog, giving a presentation is even more powerful. So now we have decided Sundays is going to be our peer learning series, right? Like how Saturdays 4 to 6 is facilitator series, Sundays we'll have peer learning series, and which is again 2 hours, half an hour for each of the teams that we have, right? Quantum hardware, cryptography, finance, and machine learning. So that's the context in which we are meeting today. So this 10:30, it's just happening today, the peer learning, which will be moved to Sundays 4 to 6 p.m. All right. So with that as the context, and assuming that all your learnings are going, and I've been interacting with almost everyone on a daily basis, I'm so glad to see this happening, and this motivates us also, right? Like it motivates everyone, and that's precisely the whole point of this, right? And when we look at So this Saturday is going to be a very interesting session. This is with Dr. Urvashi. She has been in the quantum cryptography field like her entire life, and she's one of the few people who are working on the quantum related policy for the Indian government. And she was very inspired and very appreciative of what we have been trying to do as a community. So our vision of becoming a incubation center is very close, because we are now going to be helping her in drafting the policy as well. So looks like things are happening really fast. Like most things are happening in the current scenario, right? Like everything is accelerated. Like think about this. This would not have happened this fast if it wasn't for COVID, or like people adopting, virtual technologies this quick. Let's keep this momentum going. And as in Tamil, we call it Pullayar Chuli, which is the, what do you call it in English, Kedar?
Just a starting stone, I guess.
Okay, that's said. But Pullayar is the Ganesh.
Ganesh, that thing. I don't even know in Hindi.
Okay, so basically, you start off with that woo thing, right? Like we could look at this whole session as the Pullayar Chuli for peer learning series, and we have like really, really inspiring people, Path, Nile, and Kedar with us. So Path will start with the high level, the flow and the microarchitecture, and then Kedar will talk about reversible circuits, and then Nilay will kind of like sum all these things up. Okay, with that, over to you, Path. Please take it here.
Hi everyone.
All right. Hey, a little louder.
Hey.
Yeah. Just.
Oh, sorry. Path, can you also quickly give an intro about yourself? All of you. Path, then Kedar, then Nile. Quick intro and then get into it.
Okay, so the quantum hardware team has been exploring ways for actual implementation of the quantum principles and mechanics in the hardware domain. The team currently consists of Kedar, me, and Nile. So we've been doing some outstanding ones. So now over to you, Nile.
Nile?
Nile is too happy to speak.
Oh, sorry, the mic was muted. So this is Nilay. I'm with the hardware team and we're exploring the microarchitecture part. And my even interest in quantum in the hardware is regarding the physical implementation and the hardware optimization. Over to Kedar.
Hey, so I'm a graduate and I currently work in the classical VLSI domain. So this is actually my first as a getting into the quantum realm type, except for the GSS conducted by Quiskit a month ago. So what I've been doing with along with Nila and Parth is exploring and reading some research papers and discussing what more to read, like basically narrowing it down on what is relevant and what is not, and that's what we've been discussing for the past week. And I've summarized what I have read a little bit and going to be outlining about it. So over to Parth again.
Yeah, let me just start again. So basically, why are we actually exploring quantum computation in the first place is because the prime reason would be the lack of computational power, the daunting problems would be the second, and the third part would be because actually exploring the unknown part. See, basically a classical computer works on the basis of a deterministic model of computation where it's being told that 1 + 1 is actually 2, whereas the quantum computational model works on a probabilistic model of computation where it actually determines the answer based on probability, what is the actual or most probable answer. So based on that, the TU Delft University of Technology and IBM have devised a quantum accelerator architecture. So this is the up-to-down layout of that. We'll either adopt a up-to-down approach or a down-to-up approach. Both will lead us to the same result. Now, the current IBM Q1 platform runs somewhere here in the Q arithmetic runtime and compiler layer. This is where you're actually designing all your designs. Now, some may say that we are designing algorithms or something, but that is something totally different, and it does not currently come under the Q1 platform. So basically, whatever is running, whether it's on IBM, Rigetti, or D-Wave, everything runs on the quantum instruction set architecture. So basically, what is instruction set architecture? That is the abstraction of the general operations. That is what your current processor or accelerator is performing. That whatever operation or algorithm that you want to run, it abstracts and dumps it down to a sum of some basic operations, whether it's add, subtract, some basic operation in the classical era, and its paradigm in the quantum era. So its abstraction is what we're actually dealing with, because it's something very concrete. Now, one of the primary reasons for exploring this was because we need something concrete to explore in the future, because while the country is somewhere here currently in the quantum chip, because the actual computational power comes from the computational basis. All of your current classical computers are currently binary in nature. Therefore, their computational power is measured something in the form of 2 raised to power n operations. Okay, so whereas for a quantum computer, the degree of differentiation is more. For the IBM Q1, we have a 4-degree differentiated quantum bit. That is, it's not just a binary 1 or 0. Instead, we have added the amplitude, angle, and phase. So now there are four components. So the number of computational bases are of the form 4 raised to power n, hence the greater computational power. But this quantum chip is basically for synthesizing the actual quantum bits. It keeps on changing currently in the current industry, whether it's transmon qubits or superconducting qubits or hybrid qubits. The current industry and the academia both are still exploring. And there are various ways of controlling it, whether it's photonics, lasers, microwaves. The industry is still innovating. And further moving along, we have the quantum to classical. Now, this is where the logic comes into place. The logic is that you know that in the quantum mechanics, there's something called as superposition, there's something called as entanglement. The actual hardware implementation of that logic in the classical computational era, that is the quantum to classical operations, and this is what is termed as reversible computing. Reversible computing is that you need not access the memory. Instead, you simply compute the answer you want. Supposedly, if there's an AND gate, you have an A and B input and you're getting an output C, then you can simply compute back the input from the output C. This is what the Kedar would be explaining further in the future. Moving up, we have the microarchitecture. Now, microarchitecture is the truth and the hardcore reality of any hardware present out there. Now, how do we actually define microarchitecture? Then we come back to the instruction set architecture. Now, as I said, it was the core abstraction of the entire instruction set, whether it's some operation like add or subtract. Let's just take the add operation again. If it's an AND gate with 2 inputs A and B, there would be 2 wires running from the register A and B into an AND gate, which will lead further to an output written in output C. Now, in a classical computer, this operation is termed as add A comma B. Now, this is a classical operation in maybe any instruction set architecture out there, whether it's x86 from Intel or it's RISC-V or the IBM PC architecture. These architectures have been out there for more than 50 years now, and they haven't changed because the abstraction never changed. And this is where you guys can contribute to, whether it's QML or quantum cryptography or any other team. You can just give us some basic set of operations that you perform on a very frequent basis, whether it's superimposition or it's entanglement. We can try to abstract it further and form something concrete of our own. Okay, and the actual implementation is where the microarchitecture lies. Now, this is the reason why supposedly there are 2 processors, Intel and AMD, both are using the x86 ISA, but both have a different performance. This is because the organization is different communication protocols and different implementation algorithms. So this is where we're actually working. And this microarchitecture part is what Nilay would be explaining you further. So moving further along, I guess Kedar can start with the classical implementation.
Yep.
Should we take questions now or after you guys are completely done?
I guess we can take it now, like otherwise.
Okay.
might forget later.
Piling up? Okay, cool. Guys, if you have any questions with respect to the architecture that Parth had shared, see, we are all here to learn, so there's no right or wrong questions. There's no stupid questions. So just don't hold back. KG, are you talking? You're muted, by the way.
Anyone?
Instead of audio, I clicked the video.
Ah,
Okay, my question is that quantum instruction set, right? That Q instruction set architecture.
Yeah.
Is it something similar to RISC or CISC?
Yeah, definitely. RISC and
Classical.
CISC architecture, that's what Kedar would be explaining further in the comparison between the quantum and classical ISAs. That instruction set is something very abstract and it can be implemented in a way. Kedar would be further explaining that. So I've kept that for the future.
Okay.
Anyone else? Let me just share one another picture.
yes,
Then I
yes.
guess
I was gonna
someone-
just say that. Yeah.
Yeah. So sorry. So this is the reality that you're more accustomed to. This is where all your applications are, whether it's genome analysis, AI, ML, cryptography, all is here. The logic is not actually here. This is your algorithms, which is actually lying here. The OpenQL or QSM is the assembly language or the actual, how to say, programming language, which is present in the industry. This is where the core reality lies. The ISA and the microarchitecture. This is where we're working, and we can really use some help. Now, this may be changing in the future, the quantum chip material. Now, this is still changing, but our functions or our abilities simply are restricted to the quantum operations or logic. We're not interested entirely in what IBM or Rigetti is doing, but are interested in understanding the quantum logic and bringing out useful solutions from it. With focus on that, try and explore everything. So this is basically out of a quantum accelerator. Okay. Any questions now?
Cool.
Okay, I guess we can move on with Kedar.
Yeah.
Right.
All right. Kedar.
Okay, we'll start with the reversible circuits. So in order to understand that, first we must know that in the classical circuit and computations, whatever gates we use mostly, like AND and XOR, they are basically irreversible, meaning, so for example, we'll take one of the gates AND. So if we take two inputs A and B, be it A is 1 and B is 0, or A is 0 or B is 1, we get the same output, right? So with the same output, we are not able to reconstruct the inputs from the given output. So I think Parth also mentioned this. So this is the irreversibility, this is the irreversible nature of the computation that we are currently using in classical circuits. So when we talk about reversible circuits, we mean that no such information is lost. When we have the output, we can deterministically determine the input states. So in principle, actually, this means that no heat will also be released, and basically there will be no dissipation, or you could say maximum efficiency. So there is this principle, Laundry's principle, which states that for every irreversible operation that we do, at least this much amount of energy is released, which is given by the inequality log 2 times log 2 of Boltzmann constant times the temperature, which is kind of basically based on the second law of thermodynamics. So what we should understand from this is, uh, if we look at the 2000s era and the heat dissipation in our standard computers that we used to use then, it was a million times more than this uh, basic limit. We can call this a limit of heat dissipation, which this is a theoretical limit on the reversible operations. So in the 2000s era, we were a million times uh, still behind this, in the sense the heat that we dissipate was in order of 10 power 10 or so more than the theoretical limit. just in 10 years, 2010s era, we are now just 10 power 6 times more than the theoretical limit. And it is actually expected, so this is a very vague prediction, but it is expected to reach the limit by 2050. So this is why actually even in the classical computations we are worried about and concerned about using the reversible computation techniques instead of the classical irreversible ones. So this doesn't necessarily have to do with the quantum computation, even in the yes ms.
No, that's a question by Shubham. Can you give an example of reversible and irreversible operation?
Okay, right. I'll just type it. I'll just try to type it here because I don't have that pencil kind of thing. Okay, so
You can
in
use an
a
annotate tool on Zoom if you're comfortable.
Or even you
Click
can
on the
use.
few options at the top
sorry,
bar.
I didn't.
Okay.
I didn't. Okay, annotate.
Yeah.
Right. I'll try this. Let's see
Cool.
how well it works.
Ah.
Right.
Yes. Yeah. If you're using a mouse, it should be easier. Yeah.
I'm not exactly able to get it.
Okay. Check it. Yeah. Write it. Yeah.
All right. So let me try to get a kind of a table over here, A and B, right? So
Shall I
basically in
explain
irreversible,
in the interest of time?
sorry?
Yeah, shall I explain in the interest of time? You can continue with your. Subham, not operator is an irreversible operation because it has one input, one output. Other than not operator, and has two input, one output. We can't reverse, meaning that the output and input cannot be exchanged. That is a reversible, not reversible. So in classical computing, Naught Gate is reversible gate, and or XR, those are all irreversible gates. Does it help you to understand?
No, then but then like why are they called reversible and why are they called irreversible? Like
Because in the
So-
NOT, if you change the input output, it is possible, right? You can reverse the input and output.
Yeah.
But AND gate or OR gate you can't reverse because the output only one output, but input to input. So the number of input and output itself makes clear that you can't reverse it.
I think it's like reducing input from the output. In not it is like you just have to negate. But while the other case is like you have to reduce two inputs, right? Meaning from
two
output.
inputs and one output. So reversible, you cannot have with one output. We cannot have two inputs. The other way around cannot happen.
So Shubham, so if you concentrate on this particular row, so if we have the output as 1, then we can clearly say that the input should be 1 and 1, right? So we get the inputs. But in case the output is 0, it could be 1 and 0 or 0 and 1. That ambiguity is there. So we don't know the input state exactly. So that's what he means by saying the input cannot be reconstructed from the output. So that's the irreversible nature. But in case of a gate called C0, so the operation is basically such that when A is 0, right? When A is 0, then the B bit is just propagated to C. And when A is 1, then the B bit is negated. So basically it is a NOT gate only when A is 1. And just a normal transmitter when A is 0. So the A is called the controlled bit over here, controlling bit, and B is the target bit. So here this particular gate is called C0 gate. So in this case, you can see that whatever I missed the
output we
main
get
thing
kind
over
of we
here.
can trace it back.
Yeah, so the main thing over here is that we don't just have C as the output, we also have D, because again, this will still be the same as irreversible. But in D, we have the D is basically the same as A. So we can have 0, 0, 1, and 1, basically whatever A is. So now C and D constitute the output at any time. So with this output, we can determine the input without any ambiguity. So this is an example of a reversible gate. Similarly, in case of 1-bit NOT gate, right? So if it's 0, the input is 1 and vice versa. So that is an example of reversible gate. And when you think of why we need a reversible gate in the first place, then this thing comes into the picture that this principle states that at least this amount of energy will be lost every time we do an irreversible operation. Although we are doing really great optimizations and we are bringing down the energy that are dissipated throughout the years. Uh, just within a span of 10 years, we have brought down it by the magnitude of order of 10 power 4s and all. But in the future, this we might hit this limit and there will be no more optimizations theoretically possible, even theoretically possible. And quantum mechanics actually has very stringent requirements that this system cannot lose information over time, because losing information means like when we are propagating towards the over the computation, we are basically losing states, right? So we cannot determine the output or the input. So this means decreasing the entropy, which is in not in accordance with the second law of thermodynamics. So that's one physical barrier. And also the classical computers that we have, the classical bits that we have, are all made of semiconductors. And these are basically quantum materials too. They have quantum features, they have quantum properties. It's just that, am I audible? Because I just got the message that my internet is unstable.
Yeah, it's fine. It's fine. Good.
Can hear you.
Okay, cool. So even in the classical computations, the bits or the semiconductors that we use are quantum in nature, but it's just that we are not harnessing that quantum properties of the materials and just using the classical properties. And we are basically, we could, in other words, say that we are not exploiting it fully. So in quantum computing, we will be focusing on uh, very specific particular quantum processes and exploiting them and using them as the bits instead of these classical bits. So that there, when we get down to physical quantum processes, all the processors are all the processors are reversible in nature. So that is why we need to have reversible circuits, so that we can use quantum processes as qubits. So let's come down to how exactly like what are the major gates that we use, right? So in case of, let's take a case of adder circuit or adder module for that matter. uh, Imagine a module which adds two numbers like 5 and 5 and you get the answer as 10, right? The sum as 10. So again, this is an irreversible module because the same 10 you can get using 3 and 7 or 4 and 6, and a lot of even like 12 and minus 2 also. So this is again an irreversible module. But then we want to have if we want to have this in quantum computing or quantum circuits, we might think that this is not possible. So we cannot have, but we can also have such an important module. So that's where what we do is we change the mode of operations, as in we add something to the output, we change the whole gate so that it becomes reversible. So there are some conditions to meet the reversibility criteria, and the main one is to make it a 1-1 function. So in our case of adder circuit, we can, or adder module, we can have another output which for example says the subtraction of the difference of the two numbers. So in that case, the whole module becomes reversible, because with at any time the output will consist of the sum and the difference of the two numbers, and with that we can reconstruct the output. So it's kind of like n equations and n variables. So the whole goal is to make the whole module deterministic. But then just because this module is now deterministic doesn't necessarily make it reversible, because in we need to have reversibility in all levels of abstract. So right now we talked about something like the modules of it, right? When we talk about abstractions, it could be the algorithm, it could be the high level language, or it could be the machine code. And then comes the computer architecture, gate level, and the finally physical implementation. The whole overview even Parth also just gave. So in our example, we fail over here the gate level and the physical implementation because this is not yet reversible. I have not yet talked about how to achieve this in a reversible manner. So okay, so how can we achieve this in a reversible manner? Let's take an example of the C0 gate which I just explained. And if, for example, we use the electron spins as qubits, like uh, one of the spinning states is considered as a state 0 and the opposite spin is considered as state 1, then the frequency to flip the spin of an electron also determines the I mean also depends on the spin of the neighboring electrons. So this you can imagine as flipping the bit B in accordance with the bit A, the control bit and the target bit. So I know it is a little difficult with without any diagrams, but try to follow me here. So take a uh, independent into isolated bit B, and you pass over a frequency some kind of f, so that flips the spin. But when a system contains two qubits, so the spin of bit A determines what the spin of determines the frequency required to change or flip the spin of bit B. So now we can say that the spin of bit A controls the spin of bit B. So basically this could be used as a C0 circuit, C0 gate. And in principle, the C0 gate and any single bit qubit like Hadamard gate can be used as universal gates. And what I mean by universal gate is just like in quantum, just like in classical computing, we use NAND gate. We can use NAND gate as universal gate, meaning with NAND gate you can construct any other gate and any other function required. So similarly, with just C0 and a single bit gate, you can reconstruct any function required in the whole quantum algorithms or any function that you need. So some of the types of you know this quantum gates are mainly Naught and Hadamard and C0. These are the main three gates, and also some other gates like Toffoli. I don't know how to pronounce it. Fredkin and pairs. So these are basically like, if you think of two bits in classical, you can think of AND or XOR, XNOR. So like that, when you think of two bits in quantum, two qubits, you can think of these main gates. Also, these gates could be anything. Actually, you can design your own gates based on your own requirements. It's just that these are more predominantly used. And in order to determine what gate we need depends a lot on our functions, on our application part. Like maybe QML team, they have algorithms which choose a different kind of gate predominantly as compared to the Q finance team. So that's where we might need to interact and discuss and know each other's requirements. Oh, here are the annotations. I think the color was white, so I didn't realize. Okay. So when we talk about quantum circuits, we naturally come at the some metric to decide the efficiency or the optimization of the circuit, that is known as the quantum cost. It's just a basic metric. It's defined as the number of 1 and 2 bit gates that's used in constructing the circuit. And when we model these gates mathematically, we use it in terms of we represent it in terms of matrices. And it, one thing to note is that since these are all reversible gates in quantum circuits, so these matrices are always unitary, which means the transpose conjugate of any matrix will be the same. So if you like flip the matrix like this, it will still be the same matrix. That's because from the output you can always determine the input. So that's the main concept over here. And I'm not going to be going into the details of this. I just wanted to like show you the different kind of gates in 1 bit or 2 bit, all that. So it's fine. I'll end this brief introduction. So these gates that I just showed you, to these quantum circuits using these gates can be simulated and verified using classical FPGAs also. So as I told you, yes. Anyone has a question, right?
No.
Okay, I'll continue. I'll just finish it up. Right. So, yeah. So these quantum, I mean, these reversible gates can also be implemented on FPGAs. Doesn't make the whole system reversible. As I told you, the level of abstraction matters. So here the module level abstraction is there, but still the physical abstraction is still classical in nature and irreversible in nature. So which gates to use, as I told, it depends on your vertical and your area of application. So we might need to discuss on what gates are predominantly used, and we will figure out some set of gates that benefit all. And when it comes to physical implementation, Nilay would be talking a little bit about that. So this is basically the physical property that we decide to exploit. Like I explained there with an illustration, it was an electron spin. It could be uh, like it could be the orbital state of an electron in an atom. It could be a lot of things. So I'll hand it over to Nilay to briefly go over that.
Nice.
Hey, Nilay. So do we take questions right away or after Nilay completes?
I think now, yeah.
Okay.
One question actually. I'm Raj. Just want to
Hey.
understand. Hi. Just want to understand if I know in the earlier talk, Parth said there's no memory. Is there no hardware memory as such in quantum computer?
Although it didn't go through those parts, it's not very much explored right now. Like there are abstractions like reversible logic elements with memories. So this comes under the reversible sequential logic, and that has not been explored much currently. But
Oh,
yeah, to
okay.
answer your question, technically there are there. It is there.
Okay. Gotcha.
Yeah,
Thank you.
sure.
I'm Anirudh and I have a question. I'm not exactly
Hi.
question the answer you explained, a concept you explained about the reversibility, which requires the complete, I mean the for complete reversibility, we need only heat which has not to be dissipated throughout the process, as you explained. So I think you should have mentioned the term unitarity, because if the heat gets dissipated, then the conservation of the state, I mean, I should say the, or should I say, what the norm of the state is not conserved completely. So for the unitary evolution of the whole quantum system, we need reversibility, because if energy gets dissipated, then the quantum states or the normalized condition will not be obeyed throughout the process. I think,
Okay.
am I correct? Just point me out.
Yes, I mean, I'll definitely go check this out. But yeah, you're making sense, because when heat is dissipated, these quantum systems are basically achieved at a very delicate, uh, how do I say, it? Very delicate conditions, easily disturbed. And when heat is dissipated, that will definitely disturb the system. I think that's what you're saying, right?
Yeah,
Yes.
I
Okay.
mean, that unitarity is the basic thing. The whole quantum system evolution requires unity, because all the gates, they are basically some kind of unitary operations.
Right. Okay.
Thank you.
Sure. Thank you so much.
Lovely. Nice point. All right. Guys, any other questions? Cool. Okay. Thanks, Kedar. Nile?
Hello, is the page visible?
Yep.
Yeah, so like everyone talked, like it started from the path he told about the entire structure about the quantum hardware. like how actually there's a transition from classical to quantum computation, and how actually there's implementation. And then there was an introduction about the reversibility, which states that all the operations in the quantum regime need to be unitary in nature. So there isn't any amplification, like that's why unitary is there. And reversibility is just to uh, get maximum power efficiency and get faster, because when you are able to retrace your inputs back from the output, so that helps a lot in certain areas of computation. So now I'll be focusing more like a step further, like how actually what exactly quantum microarchitecture is. So it all started like usually there has to be if you say ISA or the common micro architecture, it's like the world, the talk which are going around the world is that the quantum computation power is the power which it actually has. It's not yet explored completely, is because of the lack of the quantum hardware. That's what everyone is saying. The reason for that is there are many algorithms, there are many quantum software which are there out in the world, but the executability of those software into the real physical implementation is reduced. It's very constant in nature because of the availability and the flexible nature of the quantum hardware which is present right now. So it's taking time for developing the hardware to execute and bring about that level of scalable system and that flexible in nature. So you can implement all the quantum softwares, all the algorithms which are there into the physical implementation. So that's where there's a lack, there's a back in the quantum hardware area. Second is that there are two flows, the data flow and the control flow. So whatever the quantum softwares and whatever the algorithms which are developed, so they give a well-versed environment for data flow of the within the quantum computer. So data can be flowed very easily. But when there's control flow actually means the feedback mechanism, like how you're controlling the each operation, how you easily you execute every operation and the instruction. So that's very it's very constrained and it's very restricted because of the available state of the art. So that's where quantum hardware needs to actually accelerate, and people are working on it. So there's qubits, like probably everyone will know. So qubits are nothing but quantum bits. Like initially we had the classical bits 0 and 1 binary in nature, which are binary in nature, and we have qubits over here which can be in 0, or it's like qubits, you can say it's like storage of information which is a continuation fashion between from state 0 to state 1. So even it can be in any of the intermediate states between them. So those are there are many physical implementations about the qubits. One is the superconducting charge storage. Second is the photons, like you take vertical photon polarization as 1 and horizontal photon polarization as 0 state, and then you have the electron spin up as 0, spin down as 1, and many more. And the area which like the physical implementation which people are actually working now is the photonics, the laser part. The reason behind that is grooming now currently and even overpowering superconducting is that because when you have qubits, so when the more time they are stayed in the physical world, like the more time they interact with the physical world, that would result to more introduction of the noise into the system. So it might become about a distortion in your state, so you might not actually get the proper desired state, uh, which is there for which is there for superconducting ion traps. But when it comes to photonics, you have a photon, it just goes and it's like from less than a nanosecond or picosecond it interacts with the world and you get your results out. So compared to other physical implementations, photons, they interact for a very less amount of time with the environment surroundings. So that's why there's less introduction of the noise into your entire system. So that's why people are working more on the photonics implementation of the qubits. So like in the classical world, we talk with the amount of data stored, like ones and zeros, like you go up, look at the resistors and you see what the data is stored. So in quantum world, we talk about the probabilities, like what is the probability that your qubit will be in this particular state or it will be in that particular state. So in the classical world, you play around with the data stored here and there, whereas in the quantum world, you play around with the probabilities of your qubits. So suppose you have a qubit, it's in either in a state 1 or 0 on your superposition, and there are different percentages of it, like whether it's 10% in 0, 90% in 1, and initially the sum should be 1 in nature because it's unitary in fashion and should be normalized in state. So to play around with the probabilities and the quantum, so basically to come out, like to translate your entire algorithms into the physical implementations, you need some amount of instructions which will convey the message from your software to the hardware, like you want to do this and you have to do it like this. So these are the instructions which were majorly discovered, so which were like the measure, the Hadamard, the phase, the T, and the C naught one. Measure is like obviously like in a classical world, you can go up and look about your resistors stored, and you can see the data stored whether it's 1 or 0 in nature. But in the quantum, you can't just go and look around whether like where a qubit actually is because you cannot see it. So that's how to get the measurement, like how what in what state a qubit actually is. You put a measure. That is like you perform an instruction, like you give an instruction to the environment that I want to know the state of this particular qubit. So that means you're performing an instruction called measure. So which means you're measuring out the state of the qubit, and which results into this qubit to be in a particular state with the probability of 100. So this is what measure instruction is. And the Hadamard is like initially you might have qubits in the various, like suppose there are 3 qubits, so it can be there can be 8 different states which all these 3 qubits can be in. That's 2 power 3 8. So there can be different function, there can be different percent probabilities for the qubits q0, q1, and q2 to be in all these 3 particular states. So it can be 10, 15, 20, but either the sum, entire sum should be 1. So what Hadamard actually, what we actually do in while implementing is that it's called something called Hadamard Initialization, which means that you apply Hadamard Gate to all the qubits, which results into the qubits which are equal in probability. Like suppose if you have 2 qubits, so there can be 4 states possible. So each 4 states have like 30, 20, 20, and 30 probabilities respectively before Hadamard. But when you do Hadamard initialization, which means that you're bringing all 4 states into equal probabilities. So now each state has a probability of 25. So this gives a better, like you're not giving an external bias to your system. You're bringing all down to the same level, and then you perform your algorithms to get the results. And there's a phase which Parth talked about, like the computational basis for reversible circuits. So basically reversible circuits is nothing but the label of your instruction set. So basically
Uh,
and each and
Wait, Nile, the last 2 sentences, can you repeat? I couldn't hear.
yeah, so like Parth told earlier, like in the quantum, we have a computational basis of 4 power n, and one among them is phase. So you can represent the state and the phase of a qubit on a quantum sphere. Phase actually is like if there's a wave function like psi is equal to, so there can be probability a1 for a state of 0 plus its e power I phi. So where phi represents the phase orientation of the bit or into 1. So phase orientation tells about the what you can say, the orientation of the qubit, how it actually is. Then there's T, which is T gate is always applied like for rotational about the Z axis, the R axis, which for rotational basis. And then you have the C naught gate. And C naught gate is something called like the universal gate, because all other gates which you have in the quantum, you can implement them while varying out with the playing, like just playing around with the C naught gate. So these are the basic 5 instruction gates which are there. And then you come around to ISA, which is called instruction set architecture. So in the classical world, we have the RISC and the CISC, reduced instruction set computer, and complex instruction set computer. So like reduced is like you have reduced number of set of instructions, and like with just one instruction written, you can perform many operations. And in complex, you have like long enough amount of instructions which you need to do particular operation. So in the traditionally, we have the format to write. It's called opcode slash address. Opcode is nothing but the label of your instruction. Like suppose in a classical world, if I'm using any microprocessor or something, if I'm going to perform a move operation from moving a data from resistor B to resistor A. So I'll write move, that's MOV A comma B. So where my MOV is called the opcode, nothing but the label of my resistor. So with that, whatever your architecture actually is, it will read the opcode and it will decode the particular instruction, and then it will convey the particular information to the next step of hardware implementation. So after it's decoded, so the hardware part actually knows exactly what to do, and the address is like where you actually want to store your information. So this is in the classical part. When we come to quantum IC, that's quantum instruction set architecture, you basically, there's something called opcode comma qubit. So like suppose if I have my opcode C naught, but C naught is a 2 qubit gate. So suppose if my so then the syntax will be opcode comma qubit 1 comma qubit 2. So you will specify C naught, like whichever the label actually your assembly language is using. uh, so it will be like C naught comma q1 to q2. So that means I'm applying a C naught between q1 and q2. So that's called, it's similar analogous to the quantum IAC part. So I'll just show one. Is the PPT visible, like the picture?
Yeah, yeah.
Yeah.
Yes.
This is just the brief picture of the microarchitecture of a quantum computer. So like I said, there's instruction memory, data memory, and this actually increase, like we were talking just about the control part of the microarchitecture, but this thing over here involves the data flow also, which involves pipelining. That means after your instruction set is decoded, then the data has to be it's whatever you have, like qubit 1 to qubit 2. So the qubits are like transition, like there's a transition from one state to other state. So that represents in the pipelining nature. So as you can see towards the uh, this part, one second. Uh, yeah. This part over here, you can see this quantum instruction set decoder. So which I was talking about. So when you have the opcode comma slash qubit comma qubit, so the opcode, the instructions is actually transferred on to the like this is the classical pipeline, like the correlation, the connection between the classical computation to the quantum computation. So where your all the instruction sets from the instruction memory and the data memory, it's all pipelined over here. Then there's further, it's transferred into the quantum instruction decoder. So where your whatever instruction, like what operation your instruction performs, the machine operation which your instruction performs. So these are decoded by the quantum instruction decoder. Then there's target registers. Registers are nothing but the memory where you actually store. Over here, memory is not something like very physical in nature. It's like the states of the qubit. So the qubits are in that particular, so that represents the memory. So and then you have a microcode unit and there's a control store. Then you have a quantum micro instruction buffer over here, which is again like it combines the entire system. Then it just, the procedure just goes on, like you have different address logic, and then it's basically, then it's just still like the traditional, like how we have the controls in the microprocessor. Like there's an input, there's a instruction decoder, it decodes the instruction, it takes in the valuable operation which needs to be done. Then the control unit transfers all the particular instruction to respective registers, and the computation is just done further, and then which are all performed on the qubits, like as you can see at the end. So all these things are performed on the qubit, and then there's a way back, like this is code word triggered pulse generation, which means depending upon your operation which you need to perform, these are done like the arrows pointing towards the qubit, which means that you're performing something on the qubit. And then there you can see on the top, it's called measurement discrimination, which means that the arrows are coming from qubit to the like it's coming outward of the qubit. So which means that when you're measuring the qubit, so that the data is transferred from the qubit to the measurement system, like it's actually taking the data from the qubit. So this is the overall picture of the quantum microarchitecture. One second.
I could clear all. Okay.
Yeah, so this is just the general overview of executable QASM, which is like executable quantum assembly language, which like even IBM uses this. So these are the like just the basic instructions which are there. So there are control instructions, the data transfer, the logical, the arithmetic, and the other. It might seem very familiar with the instruction which we have for like general microprocessor 8085 or the ARM processor or many other like basic operations is just the same. And what instruction set actually does it, like whatever you need to do, you write it in an algorithm, like you write it in a program, and then you compile it on a simulator or something. And then what actually architecture does it, like it converts your software written, like your algorithm code, into a particular language which the physical, like the hardware system can understand it. So it's basically converting your high level assembly language into something which a hardware system is able to understand and then further execute the system upon. So this was the overall picture about the quantum hardware, like with the microarchitecture. And to add on, it's just that like things are like people are much exploring, and what like the entire quantum hardware team would like we just need to take insights like from the other verticals, the machine learning, the cryptography, and the finance vertical, is that while defining these particular instruction sets, like when we have traditional quantum Fourier transform, and if we have like making up a Bell state, so we can have predefined instructions. Like you need not write the code to make a Bell instruction. Like you know, like if you have a 2 qubit, like you need not write a code to put those qubits in a particular Bell state. Like don't need to write up a code. But if we can put up a like make up our own instruction and define the entire thing in a such a way that you just need to use like the opcode Bell state, whichever state you want, and then the qubits number. So that would actually reduce the work on the programmer side, and this would be like extending it. So we have predefined instructions like for quantum Fourier transfer and many much more. So what quantum hardware team would like to know is that the frequent instructions or the frequent operation which the other verticals use while programming, and if we can deduce them into a generic instruction, like that would be like something of our own which we have developed, like so that would even reduce their effort on their side, and we can even come up with something of our own. So I'll conclude mine now. So any questions?
Can you stop sharing?
Yeah, sure.
All right, great. So while we wait for question, let me quickly talk about what's in store tomorrow. So tomorrow, 10 to 11 will be, because all three of you hinted upon the fact that, you know, we want to work with either the QML or the quantum cryptography or the finance team. So quantum finance team has been working on a couple of use cases, but let's talk about one for now, which is options portfolio optimization, right? Like if you've read the Gartner's report, quantum finance is the first industry, or like finance is the first industry that will adopt quantum technology. And we have been working on that for the last 4 months. Now, so now that we have more people and we have people on the hardware side, I think it makes only logical sense to combine these two things or see how we can collaborate better, right? So tomorrow, 10 to 11, the entire quantum finance team will be here. The first half an hour will be the functional aspect of what we are trying to do. That will be given by Pawan, one of the partners of QCI. He's also a patent holder, algorithmic trader, worked with Infi for quite some time, solutions architecting. Now he's full-time into trading, okay? And so he found this use case which I really think is something no one else in the world is working on right now. So it's a very, very interesting use case. First half an hour will be explanation of that use case, and second half an hour will be by KG, who will take us through the technical architecture of whatever we have done till now. And then I think we'll see a lot of synergies, right? Like you guys can put on your hardware lens and then see, where you guys can come in and help. Probably others also, people who are working on QML, quantum cryptography can pitch in as well. So it'll be very interesting tomorrow, 10 to 11. I'll send notifications, whatnot on Discord and everything. But like tomorrow, 10 to 11, we'll start talking about quantum finance and see how we can work together on that. All right, cool. And on top of that, just for quantum hardware team, so we are talking to Professor Shine. Professor Shine works with IISc, and he is his expertise is in data storage, right? So he is someone who has been working on QRAMs, like quantum RAMs and stuff like that. The head of IEEE, a lot more institutions, right? And he is going to be on our advisory board, and he'll be overseeing quantum hardware vertical. All right. So these are two things for the quantum hardware team to look forward to. One is tomorrow, where we can talk about how quantum finance and quantum hardware can work together. And slowly we'll get into pure research angle as well once Professor Shine joins us. All right, cool. I saw a couple of questions. Let's quickly take that. Yeah, tomorrow 10 to 11, right, Kashyap? Okay.
Let me just sum up from Nele to Nele. Can you share the slide of the QASM, please?
Sorry?
Can Nele share the slide for QASM, please, which you are sharing the last slide?
Right. Nele?
Yeah, just a minute.
Does that effort need to be done for all industry? Which effort done more? The finance thing you're talking about?
No, the previous one only. Yeah, that's it. Okay, so basically the info we wanted from every team is there. You can see the type and control. Whereas this is the type of the instruction, whereas arithmetic, logical, transfer, control. So basically, supposedly, say if it's QML, then we know that you run a great number of regressions and optimization. So perhaps come up with something in this domain only, the type that you want to generalize. Okay, the one you use on a frequent, not the entire instruction, but the basic operation, the generic math that you want to use on a lot of basis. Okay. So that's it, my side. Yeah. Okay. And stop this here, Nilay. Thanks.
Nice. Nilay, did you see the Anmol? So this question is related to, does that effort need to be done for all industries?
What? Can you elaborate on it? Like,
yeah. Is there a database for storing quantum information?
There is no database for storing the quantum information, because then again, for the classical computation only, the major constraint in non-classical processes is that you need to deliberately go and fetch the memory or write the memory that you need. What quantum computing provides is that it computes whatever it needs at that very moment. And it simply builds on that using probability that, yes, it should be the most probable answer. So currently, we do not maintain a database for quantum information.
So is it in-memory calculation?
Sorry?
Is it in-memory calculation? Like you say, it doesn't store the information.
See, currently it's not storing information, because when we talk something like a quantum memory or memory in general, we run into something called as the state space explosion problem. Whereas the data is so much, or it's so large, that the memory will run out. No classical memory currently exists which can hold this data. And as for the major operation which Nilay mentioned, which is actually whatever operations they're performing on the quantum bit, those are inserted in the active time. But when you measure, that is simply by collapsing the qubit. That is, if we'll measure the same qubit at the same instant multiple times, and when that particular instant delivers that particular state, that is the correct answer. You can read up with Bloch sphere. That should give you a better visualization of the quantum bit. Read up on Bloch sphere.
Okay, thanks. Regarding first question, you mentioned that you need to do a lot of let's say configuration or programming at the hardware level, and you are with the finance problem. So what I meant to say, for other industries, like if you want to do for insurance or telecom, then do you need to write some special program in the hardware?
No, we don't need a special program. See, supposedly if it's telecom will dial it down to the DSPs and conventional, there's digital signal processor. Whether it's analog or digital domain, we'll simply put it into the classical operation. That is where the domain of Kedar lies currently. The quantum to classical operations, we have said it as the reversible logic, but its actual operations lies in controlling the quantum computer currently. See, if it's the IBM Q1, you might be sending signals here in the form of digital signals. There it's being converted to either microwaves or photonic signals. So that is the job of the classical operations or reversible operations. Yeah.
Yeah, the quick question here. When it comes to hardware or maintaining the temperature, what I understand, it's a very low temperature that needs to be maintained.
Yeah, the qubits need to be immune from noise. Yeah.
But then do we have that kind of environment? Because it's going to be extremely low temperature, right?
Yeah, it's 15 millikelvin and quantum computer which they have made. So they maintain like the quantum computer is like the last qubit part. It's stored at the bottom of the, like you can say, the refrigerator. So it's in the bottom, and that's the temperature at that particular state is 15 millikelvin. So it's there, like it's possible.
We can maintain that temperature, but as I said earlier, the quantum chip part is still being explored by the academia and industry, and it's still progressing. The actual immunization of noise from temperature, it's not the only way of controlling noise.
Okay.
Because photons are obviously progressing very fast, definitely.
Right, because the interference would be a lot, right? Even a minute,
Correct.
Any minute thing also would completely move the entire thing.
Absolutely, it would tamper with the actual state of the qubit. That's why the industry is coming up with more number of models, and that way is more of a probabilistic answers not taken in one go, but multiple runs are being conducted on the same qubit state.
Okay, just an extension to that. So, so when we are trying to do it from classical, what we are doing is there is a data stored, we pull it out and do the computation on that. Whereas it comes with quantum, we really don't have, as you said, it's a probabilistic thing. So then how, when we're doing a computation, are we trying to get the data from somewhere, or data is generated, and then how is the computing going out, in and out?
The data is put in the form of analog signals or the wave functions.
So that's,
and as for the output part, the memory, supposedly, let's just take a classical example from Kedar only. If it's the Naught Gate, we say that Naught Gate is a conventional reversible gate. But in practicality, we don't simply just take the output from that particular output terminal only. Instead, we insert an entire reversible circuit below that particular input circuit, and then we extract the actual output from that circuit. So reversibility is a term that is still being explored in quantum logic. So the memory part is still very volatile, whether we do need memory or not, because the moment you collapse the qubit, all your operations are meaningless from that moment on, whatever you performed earlier.
okay. Thank you.
Okay, somebody has posted a very long question. Nile will take that.
Mm, well, I guess I'm not well versed with the gravitational waves, like how do you actually come out with the computation with? Like I haven't read much about it. Like if someone has else done, like when you don't know something, what actually how to measure it, I can't comment like what hardware changes we need to do. So I guess I can read about like if you can tell like how do you actually measure gravitational waves, like apart not from the YouTube video, we have the elastic thing and the stone moving around, we see the waves. Hello, yeah, Archit, am I audible? If you can explain like how do you actually measure, then I guess we can think of it.
Yeah, so Nilay, Kedar, and Parth, thanks a lot for giving this nice session. So talking about how do we measure gravitational waves? So they are measured by the LIGO detectors. So they use the concept of interferometry. And in a nutshell, if I say so, when gravitational wave pass through the place where you're sitting, if a gravitational wave pass, so it actually has two types of polarization. So either it stretches you in up and down the place, and it contracts you in the horizontal plane, and that is one type of polarization, or it will be a diagonally polarized. So because it is stretching and contracting you in space, so there is a physical difference between the distance the light actually travels in the interferometer, which is used to measure. So these are like 4 kilometer long, highly vacuumized tubes, which have the laser, and then the when the waves pass, so there is the difference causes a phase difference between the lights being interfered, and which actually causes an interference pattern at the photodetector. So this is the basic concept which goes with the LIGO detectors. So why I posted out this question, because right now actually me and one of my friend are writing a paper, research paper, to actually integrate quantum algorithms into this kind of process. So this there is this major, like there is this major block in our further process, that uh, we know what to do, but uh, I think there is this limitation of hardware. I don't know what, because I don't know much about hardware right now, that it is preventing us to actually integrate these two fields.
I can give you a view from my side. I worked on the project of SETI. It's Search for Extraterrestrial Intelligence with the University of Berkeley. So there we were characterizing some gravitational waves and deep space data only. So I'll say from a quantum perspective, we were conducting signal characterization beyond amplitude phase and the basic signal that you're familiar with. But if it's strictly confined to gravitational waves, I guess it would be something called as a quantum analyzer. We have a logic analyzer in electronics, but a quantum analyzer would be something that should be restricted to gravitational waves. Then you can look into it, or perhaps you can share what you want to convert, then we can give our input.
More or less, like what I guess is like in the gravitational wave, like the LIGO detectors, that the whatever detectors are, they are measuring something which is already there. Like yeah, it's like just with the change in the environment which they provide, they get to know. But I guess in the quantum computer, like the quantum hardware, is like you're creating something which you want, like you're creating that particular state. So you're making something. So I guess there's the difference between like when you're measuring something which is already there, and in the quantum way, like you put the qubits in those particular states. So that's a difference. Like Parth said, like we need something like quantum analyzers. Then I guess that's all. That's my
I
view.
guess we can copy from whatever data that we're getting. That was what we were getting. We were getting a lot of earthly noise in the SETI project. So this is something, the quantum computation can go beyond the usual signal analyzation parameters. Then you can further look into it, but we need to know more definitely.
Yeah, actually, like it is kind of an open-ended question right now.
Sorry?
It is kind of an open-ended question right now.
Yeah, definitely. CMOS, Kedar can take it. Kedar works in CMOS.
What is CMOS technology? Right. Okay, so currently all the bits and computation that we do. Okay, let me actually tell you what technology is. So you must have heard about the bipolar junction transistors, right? BJTs. So with three terminals, one terminal controlling the transmission of the other two terminals. Basically, in this case, the resistance between the other two terminals. This kind of creates, enables us to use it as a switch, and this is when used as switches can be known as BJT technology. And CMOS is not very different. It's also a transistor. It just happens to be, the three terminals happen to be uh, on a like actuated on a different level, because like in BJT, it's basically when you fuse the N P and the N semiconductors together, and in CMOS, it's the metal oxide in between the semiconductors to create the charge gap. So this is a totally separate vertical into itself, but not exactly related to quantum. And I guess the videos would be able to explain in a much better condition right currently, because I was not prepared for this question exactly. Like otherwise, I can do one thing. Tomorrow, I can have some kind of like props or something to explain it to you. So that's easier.
Well, I guess we can have some sessions where every particular, like the people are from different domains, like the personal domains. They can come about with like some 5 minutes presentation and they can share their knowledge. Like, will that be good?
Yeah, 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 yeah. We'll do that. Also, this is, I mean, the whole point of peer learning is to get better at teaching also. You know, why Richard Feynman is so effective as a physicist is because also he's a great, I won't say teacher, a great show teller, right? Like he's a storyteller at the end of the day.
Yeah.
Yeah, because like now Kedar said, like I'll hack something to show it to you, and I really liked it. If you can really do that, that'll be awesome. Okay, cool. Lovely. This was nice. So tomorrow, 10 to 11, it's quantum finance team. So, I mean, because we are learning in silos right now, now we are trying to bring all these things together, right? And it's been just 1 week and we have already reached that stage, which is great. And let's keep this going. And this Sunday, we'll have a quantum cryptography team and quantum machine learning team. Hardware team is like, do you guys want to present this Sunday as well? No? Okay.
We'll give others a chance.
That's a good way of saying no. All right, cool. And quantum machine learning. Okay. Now, quantum finance will happen tomorrow itself. So QML and quantum cryptography team can take a little more time. Saturday is a very interesting session. If you guys are part of Discord, you'll come to know. Discord has kind of become our go-to instant communication platform. So I hope everyone is over there. If you're not, please ping me or KG or Shadab, anyone. I'm assuming either you're on Discord or on WhatsApp group, because we didn't promote this anywhere else, right? All right, cool. So tomorrow, 10 to 11, quantum finance, and we'll see you guys tomorrow. And tomorrow is more on use case discussion and like taking it ahead. So this hack series that we have been doing for like the past 4 months, now this will accelerate things. All right. All right. Thanks a lot, guys. It's Monday night, and then we are all here.
Great work, team.
Yeah.
Thank you.
Right.
All right. Thanks a lot. Lovely.
Am I
Bye, guys.
right?
Thanks, everyone.